In the example in the quiz, the math says the result should be 1.0, but the code says 0.95. That's a big difference. Go ahead, replace the 1 billion with just 1, and you'll see that the error becomes very tiny. We're going to want the values involved in the calculation of this big loss function that we care about to never get too big or too small. One good guiding principle is that we always want our variables to have zero mean and equal variance whenever possible. On top of the numerical issues, there are also really good mathematical reasons to keep values you compute roughly around a mean of 0 and equal variance when you're doing optimization. A badly conditioned problem means that the optimizer has to do a lot of searching to go and find a good solution. A well-conditioned problem makes it a lot easier for the optimizer to do its job. If you're dealing with images, it's simple. You can take the pixel values of your image, that are typically between 0 and 255, and simply subtract 128 and divide by 128. It doesn't change the content of your image, but it makes it much easier for the optimization to proceed numerically. You also want your weights and biases to be initialized at a good enough starting point for the gradient descent to proceed. There are lots of fancy schemes to find good initialization values, but we're going to focus on a simple general method. Draw the weights randomly from a Gaussian distribution with mean 0 and standard deviation sigma. The sigma value determines the order of magnitude of your outputs at the initial point of your optimization. Because of the softmax on top of it, the order of magnitude also determines the peakiness of your initial probability distribution. A large sigma means that your distribution will have large peaks. It's going to be very opinionated. A small sigma means that your distribution is very uncertain about things. It's usually better to begin with an uncertain distribution and let the optimization become more confident as the training progresses. So use those small sigma to begin with. Okay, so now we actually have everything we need to actually train this classifier. We've got our training data, which is normalized to have zero mean and unit variance. We multiply it by a large matrix, which is initialized with random weights. We apply the softmax, then the cross-entropy loss, and we calculate the average of this loss over the entire training data. Then our magical optimization package computes the derivative of this loss with respect to the weights and to the biases, and takes a step back in the direction opposite to that derivative. And then we start all over again. Repeat the process until we reach a minimum of the loss function.